2x over the quantity x squared minus 1. So if we're looking for asymptotes and end behavior, so everyone in the asymptotes, I should start and I should think about how can I factor this? If I can factor the denominator, I can look for my vertical asymptotes right away. So we look at the denominator and the difference of squares. So factoring into x plus 1, x minus 1. Then, once we have this format right here, quantity 2x over x minus 1, x plus 1, what we'll recognize is that there's no holes in this graph. Ben, why aren't there any holes in the graph?
Because there's factors in the bottom, the denominator.
Okay. Why aren't they holes though? Sometimes those factors in the bottom could become holes. Why aren't they, Mike?
Is it because there's no coefficients?
Not the coefficients.
There's no cancellation.
There's no repeated factor from the denominator also in the numerator. Remember, only time that there's going to be a hole is if a factor repeats itself in the numerator and the denominator. And you can cancel them out. And that's a hole in the graph. Because there's no x plus 1 or x minus 1 in the numerator, we know that the quantities x minus 1 and x plus 1, those factors, when set equal to 0, give you the vertical asymptotes. Okay, so these are vertical asymptotes right here. Again, had they repeated themselves, which we're going to see in another example, we would indicate that that's a hole, and then we'd have to find the y value of that hole. Okay, or the y height, not really value, because it has no value. Next, if we have our vertical asymptotes, so that's one down, vertical asymptotes. What other kind of asymptotes exist? Horizontal or? What's the or statement for? You could either have horizontal or you could have something else. What's the other kind of asymptote? A slant asymptote. Now, if you don't recall this from your homework or from the notes, write it down. You can either have a horizontal or a slant. You cannot have both. Again, you can't have both horizontal and slant asymptotes. To do that, what we want to recognize is look at the degrees. Ryan, what's the degree of the numerator?
2?
Nope.
No, 1.
Why?
Because it's only x, it's only x squared.
Good. So you're looking at the exponent, correct? At first you had said the coefficient. The exponent is a 1 in the numerator, so the degree of the numerator is clearly going to be 1. The denominator's exponent? Yeah. So the degree of the denominator is 2. So we look at this scenario, and when we have a case where the denominator's degree is bigger than the numerator's, or you could say the numerator's is less than the denominator's, whenever this happens, and this is our table, we had a table of 3 possibilities. The degrees are equal, the degree of the numerator is bigger than the denominator, or the degree of the denominator is bigger than the numerator. Whenever the degree of the numerator is less than the denominator, we have a horizontal asymptote and y equals 0. This is always the case. Always, always, always. Yes, there's bagpipes going on outside of here. Okay, that's always the case there. Now, had the degrees been the same, you look at the ratio of the leading coefficients. Had the degree of the numerator been greater than the denominator, you can use either synthetic or long division to find the slant asymptote. We're going to see this in the other examples, but you need to put together everything we've done so far in these questions. Next, so we have asymptotes and holes. There's no holes, we said already. We've got our asymptotes, and I'll circle them. One is here, here's a vertical asymptote. Here's another vertical asymptote. Here's a horizontal asymptote. Okay, they're all circled in black. Those are the 3 asymptotes. All right, the next step, I want to figure out my intercepts. So how do I find x-intercepts? To find the x-intercept, I set y equal to 0. So again, to do this, we set y equal to 0. That's the y-intercept. For the x-intercept, we set y equal to 0 down here. So we set this equal to 0 down here. And what we'll recognize is that we get 2x over the quantity x minus 1, x plus 1. And I forget who answered this question in class the other day. Somebody, who was it that answered this? How could a fraction be 0 was the question that was posed. Remember, how could a fraction ever be 0? If what? If the numerator is 0 only. So we don't care about the denominator at this point, so get rid of it. You can think of it as multiplying by x minus 1, x plus 1 on both sides, and that makes that 0. Or you could just recognize that the numerator has to be 0. So set the numerator equal to 0, and then solve. So here is your x-intercept. Well, if that's your x-intercept, what else do you know? It's also the y-intercept. Remember, the origin is both an x and a y-intercept. That's the characteristic of the origin. It's both x and y-intercepts. So if we look at this, we go back to the original equation, plug in 0 for x to find the y-intercept. You're going to get 0 over negative 1. Right? You're going to get this right here. You end up with 0 over negative 1. Well, in that case, it's just 0. So the y-intercept and the x-intercept are the same thing. They're the same because it's the origin. It's the only time that happens. They may coincidentally both be the same. Another time they might both be 7 or 2. But that would just be a coincidence. Here, it's not a coincidence. It's the same exact coordinate, clearly. So we've got an asymptote that's vertical, or two vertical asymptotes, a horizontal asymptote, no holes, both intercepts, and then last and not least, we have to take a look at any points on the graph. Don't go to the next slide yet. Okay, don't go to the next slide. Just kind of scroll down and give yourself a little bit of room at the bottom. Draw yourself a little tiny sketch of a graph down here. Now on your graph, draw what you know already. Draw your asymptotes with dashed lines. Draw your intercept with a closed circle. Any holes would be an open circle. So literally sketch what you know on this graph. So the red lines are all asymptotes. One is a negative 1, one is a positive 1. So this is an asymptote, x equals negative 1. This is the asymptote, x equals positive 1. This is the asymptote, y equals 0. The red horizontal asymptote that's overlaying the x-axis. What has this done for me? What this done is the following. We have now sectors or regions of the graph. We've taken our graph and kind of split it up with these asymptotes that are like boundary lines. And what this allows me to do is understand that the shape of this is going to be contained in these little regions, somewhere in these regions. So I want to then plot my intercept. So I only have one intercept here. So it doesn't help me too much. The intercept is the origin, so put a dot at the origin. So the asymptotes are, again, what are they? They're guidelines. They're guidelines. So what this tells me is the following. I need some points now, because I clearly don't have no information really as far as the shape of the graph, right? All I know are my guidelines. So using these as guidelines, pick some values between 1 and negative 1. Pick some values outside of 1 and negative 1 for x. And go ahead and try them in a table. Okay, so we have a table in the next slide we're going to look at, but give me suggestions. What are some values you would pick between 1 and negative 1 that might be easy to plug into a calculator? Or anywhere, really.
0.1.
Okay, 0.1, that's fine, 0.1. 0 we already have, which is 0, 0. Yes, you can usually use 0.
0.5.
I'd go with 0.5, maybe 0.75. What would you probably go by? Maybe some sort of increment, right? So what would you say those are going by? Yeah, by 0.25. By 0.25s. Okay, by quarters really. Okay, use quarters. Don't use thirds. Don't use thirds. It's annoying, right? 0.3333 repeating, you have to worry about it. Use quarters. So maybe when you're plugging in points, pick values, increments of quarters. How about outside of 1? Outside of 1. Yeah, you could just go 2, 3, 4, 5. Now, what you'll recognize is as these graphs, as you become more familiar with the graphs, you want to pick points very close to the vertical asymptote. So you can see how the graph shoots up or shoots down. So maybe do 1.5, then 2, then 3, then 4, then 5. But give yourself an extra one close to the asymptote. Remember, as the function goes toward the asymptote, it becomes bigger and bigger and bigger, or smaller and smaller and smaller, meaning more and more negative. But it slides along the asymptote. So we need some numbers that are close to the vertical asymptotes. So let's take a look. Okay, so what you're going to recognize here is exactly what we were talking about. Notice outside of 1 and negative 1, take a look at my values, just what Luca had suggested. I started with 1.5, but then I went 2 and 3. Over here, I started with negative 1.5, but then I jumped to negative 2 and negative 3. And take a look inside, what did I choose? I went by 0.5, but then I chose 0.25, as you guys had suggested, as increments in there. So this is my middle region of the graph. See in blue there? That's literally this blue region in the middle here, or between the two blue vertical asymptotes. So look at this region in the middle. The graph from these points is shown right here. How do I know this is here? It's the origin. That was my x and y intercept. The blue vertical lines are the vertical asymptotes. The red horizontal line here is the horizontal asymptote. These are my points. Look at my y values. I've plotted them on here. And I can see the shape of this graph. Okay? Next, outside of this region, what I'll recognize is that my positive values yielded all positive values that decreased more and more. So this graph is a decreasing function. There's 1, 2, 3 points. Those 3 points are these 3 points right here. And then over on this side, these 3 points from here come from these 3 over here. I will allow you to use a calculator. Yeah, I will. So you could actually just check this graph too, obviously, right? You could check what the graph is and see that the graph, if you graph this function, actually do that right now. Go to y1. Go to y1. In y1, type in parentheses 2x, close parentheses. The original function is 2x over the quantity x squared minus 1. And always plug in the original. Don't plug in the factored form or the simplified form or any of that stuff. Always plug in the original. Because if you made a mistake factoring and you plug in the wrong thing into y1, you're going to think it's right, when in reality the mistake was in your factor. So don't plug in the factored form. Okay, make sure your 2x is in parentheses, please. And make sure x squared minus 1 is also in parentheses. You're probably not going to see the vertical asymptotes or the horizontal asymptote on there as much, but it might be useful to zoom in with your windows. Look at my window settings right now. What's my x min and x max according to this graph?
4, -3.
Yeah, or I was around -4. Go from -4 to 4 on the x scale. So hit window. Everybody, window. Make your x min -4. Make your x max +4. Along the y-axis, do the same thing.
What is in that XSCL? That's like under the...
That's the increments, your scale.
Oh.
So if you want to go by 1s or 2s or 3s, how often you want those tick marks? 1s are fine for now. Okay, if you're zooming in on something now and you're graphing something from like 0 to 2, you might go over 10 at a tick mark, right?
Yeah.
So the x scale would be 0.1 in that case.
Right.
So for my x min and y min, x min and x max and y min and y max, I would use -4 to 4 for both. And take a look at what your graph comes out to be. It really is useful, guys, to have this in front of you. So for those that forgot theirs for some reason, take a look. And that's what it would look like. Very similar to what we have up there. Look at Ellen over there. Luca, look on, please. Okay. The shape, the general shape of this graph, you should be able to see in your calculator. Okay, does that make sense? So there's 4 steps to this one, right? 4 steps. We're going to go with asymptotes, holes, intercepts, and any possible. So let's look at this second one now. Let's look at this second one. Anybody want to step us through this? Maybe the whole problem, one step at a time. You could read through the notes, obviously, as you're doing it, but explain what's happening physically here. Starting with asymptotes, though. Nice and slow, okay?
The first thing you want to do is you factor x squared minus 9.
Mm-hmm.
You got x minus 3, that's plus 3 on the top, and 2x squared plus 1. And,
Why are there no holes?
because nothing cancels.
Okay, nothing, little louder. Nothing cancels, good. Sorry, everybody can hear.
So then, I'm not seeing any way you would factor the bottom.
Correct. You cannot factor the bottom. If you can't factor the bottom, just set it equal to 0 to find the asymptotes. So what happens though when you do that?
It's 1.
Not 1.
But, oh, so that's 2x squared equals negative 1. Negative 1 half equals x squared. That's imaginary, so.
Yeah, that's the problem, guys. So we're going to get an imaginary answer when we go to try and figure out the vertical asymptotes. Well, you can't have imaginary vertical asymptotes. So it turns out this graph, there are no vertical asymptotes at all. There are no holes and no vertical asymptotes. Continue.
So the degrees of the numerator and denominator are the same, so you have a horizontal asymptote at 1 half.
Where does the 1/2 come from?
It's x squared over 2x squared, so that's 1 over 2.
Yeah, so remember, when the degrees are the same for these two, x squared and 2x squared are the same degree, we look at the ratio of the leading coefficients. The leading coefficient of the numerator is 1. The leading coefficient of the denominator is 2. So y equals 1/2 is our horizontal asymptote. Continuing.
Then you have to find the intercept, so you start at y-intercept and plug 0 in for the x. That just becomes negative 3 times positive 3, so that's negative 9 over 1.
Negative 9 over 1 is just negative 9.
Then x-intercepts is x equals 3. It's 3, 0, negative 3, 0, since you've already got it.
Yeah, so you take the factored form up here, take the numerator, look at the factors, set the numerator equal to 0 right here, and you get your x-intercepts. So we've got asymptote, no vertical asymptote from this one, doesn't help us at all. We've got no holes, we've got a y-intercept, and we've got an x-intercept. Clearly here, we're going to need some points, right? We don't have enough information at all. So first, make a mental sketch of this. And the mental sketch doesn't help us much. The mental sketch is the graph on the left. Why am I calling this a mental sketch? Why am I saying a mental sketch? What do I mean?
It's like the graph you can get with the information you have.
Exactly right. It's the graph you can obtain mentally with the info that you have. So the info that we have right now is the following. The horizontal asymptote is at 1/2. Well, here it is, the dashed red line. The x-intercepts are negative 3 and 3. The y-intercept is down here at negative 9. So that's all the information that I've got. Again, this is literally all I have so far. So I need more points. Now, there's no vertical asymptote, but I have to figure out how to connect these lines. I don't know, maybe these lines connect like this. That would be absolute value graph. That's what that would look like for an absolute value graph. Or maybe these lines connect like this. Or maybe they loop, let's say they come outward a little bit further. We don't really know. We don't know the curvature. We don't know anything about the information there. So as a result, we cannot really graph these. But what we can do is we can plot some points. Forget the table for a second. Pick some points and give me reasoning as to why you would choose those points. What are some points you would use here and why? What are some points and why? Sabine, tell me some points you might use to choose to plug into a table that might help us to graph. -1, I would agree with. What else? 1, okay, keep going. Agreed. Would you use -3 and 3? Why not? We already know that they're x-intercepts. What else would you then choose maybe? Maybe 4, yeah. Okay, and -4. But that's really, for the most part, as far as I go, maybe choose 0.5 and -0.5 in here. as we get closer to see what's going on near the y-axis. So let's take a look at our table, and that turns out that's exactly what I ended up using, okay? Negative 0.5 and 0.5, negative 1 and 1, negative 2 and 2. What do you notice about your points? What do you notice you have in this graph?
Oh, it's
What is it?
a mirror.
It's a mirror image. You have, what is it called? What's the term? Reflection across the y-axis. Okay, so you have vertical symmetry. There's vertical symmetry in this graph. Look at the points. You can literally see it. Okay, vertical symmetry. Now, if I plot those points, I'll see the vertical symmetry that is shown on the graph. Okay, so I have in this case like a valley kind of shape. Now, all I know is that over time, this graph will eventually get closer and closer and closer to this horizontal asymptote. It'll ride alongside of it, getting closer and closer. Maybe it'll cross it, and maybe it'll go back and forth and teeter off. We don't know. We'd have to have more information and plot more points to figure that part out. Okay? Any questions on this? Does the concept make sense? All right, so what I want you to do now, okay, work with at least one other person. There's 9 of you, so there could be a group of 3, that's fine. Or 3 groups of 3 is fine, actually, if you want to do that. But go through example 3, and then I'm going to come over and I want you in the group to explain it to me. Okay, go through example 3 with somebody, and here's 2 other people. What's the header?
Thanks, man.
I sorry,
When you've gone through the whole thing, I'm going to come by when you explain it to me. So let me know when your group is done. And I'm going to ask both of you to explain it. So taking a look at example 4, we begin these just like we began the last one, which is by doing what to everything? Factor. We start with factor, always please. Now, once we factor, we can identify some things right away that might jump out at us. What jumps out at you? There's a hole. Okay, the x plus 7 should jump out right away. We're going to clearly see a hole in the graph here. Now, if that is true, the fact that negative 7 makes it 0 over 0 is indicating where a hole lies along the x-axis. Again, what would cause this to be 0? What would cause this to be 0? It would be negative 7. If you get 0 over 0, that's what a hole really is, if you remember. So if you plugged in negative 7 into the original function, h of x, you would get 0 over 0. That's what a hole really is. So negative 7 is where the hole occurs. To find the location, then we have to simplify this. So cancel these. Write the reduced one, x minus 4 over x minus 2. Then take the negative 7, plug it in here. So do h of negative 7, plug it in here. Get negative 7 minus 4 over negative 7 minus 2, giving us negative 11 over negative 9. 1.2 repeating. So there is the location and the height of the hole. Again, on the graph, what would that look like? What would it look like when you graph this in the end?
It's on the line, it's the direction, the circle, on the line.
Yeah, but what kind of a circle?
No,
Open circle. Excuse me. It's an open circle on your graph and there's a hole always. The idea, the concept is that the graph is continuous, and then it hits a point of discontinuity. Remember, vertical asymptotes and holes are called discontinuities. You should know that vocabulary for sure. Discontinuity. A function that is continuous means that you don't have to pick up your pencil as you follow along, or there are no points that make the function undefined. With points of discontinuity, such as holes and vertical asymptotes, the x value of that location would cause the function to be undefined or indeterminate. God bless you. Okay, the hole makes it indeterminate. The vertical asymptote, in this case, would be 2, would make it undefined. So there's only one vertical asymptote, and that's at x equals 2. How do I get that? Where does that come from again? Where does this come from right here? Where does x equals 2 come from? Brian? Look in the function. Look at the factored form. Come on, make a educated guess. Yeah. Remember, to get the whole, which was a discontinuity, we had x plus 7, and negative 7 is what caused that would be 0. Well, what would cause this factor over here to be 0? If x were equal to 2, that factor would become 0. That's what causes an undefined value, or discontinuity in the graph. So x equals 2 is your vertical asymptote, because it makes your other factor in the denominator 0. Okay? Now, we look at the next statement. Since the degrees are equal, how can I conclude that there's a horizontal asymptote at y equals 1? Why am I allowed to do that? What tells me? When the degrees are equal, what's our general rule? When the degrees are equal, What is the general rule? If you don't know this, you should be quickly looking at your table. Your table was in like 9.2, I think it was, or 9.3, 9.2. Sabine? Good. The fraction or the ratio of the leading coefficients. What number is here? And here? So 1 over 1 is going to be y equals the leading coefficient of the numerator over the leading coefficient of the denominator. It's not least common denominator there, okay? Leading coefficient. Leading coefficient of numerator over leading coefficient of denominator. That is the general rule you use when the degrees are equal to one another. Those three scenarios need to be memorized. You don't want to be plugging in infinity and trying to figure it out in this. You should have those memorized at this point in time. If the degree of the numerator is less than the denominator, it's simply y equals 0, also known as the x-axis. If the degree of the numerator is greater than the denominator, that was the last example, where we have a slant asymptote, and we can use synthetic or long division to figure out what that slant asymptote is. So at this point in time, we've done asymptotes, holes. What's next? Kelly? Kelly? X or Y intercepts. Good. Intercepts in general. Okay, let's go ahead and figure out the intercepts now. So we jump down to the y-intercept. We find the y-intercept by setting x equal to 0 or simply by looking up here. Look at the ratio of the constants, always. It's the easy way to do it, because when you plug 0 in, these all drop off. So negative 28 over negative 14 is just simply 2. So the y-intercept is 0, 2. Notice I write a coordinate, not simply a value of 2. I write the coordinate out. When searching for the x-intercepts, we have to recall that x plus 7 was a whole. So really what we do is we look at the simplified form only for the x-intercepts. So here's what we look at now, down here. 0 equals the quantity x minus 4 over the quantity x minus 2. What makes a fraction 0? I've asked this question like 4 or 5 times in the last week. What makes a fraction 0? The numerator equals 0. So since this fraction is equal to 0, set the numerator, which is x minus 4, equal to 0, giving us 4 for our x-intercept as a coordinate 4, 0. So we've got asymptotes, holes, intercepts, and last but not least, before we go on to points, we can make a mental sketch. Okay, we'll get on to points in a moment. There's our mental sketch. That mental sketch gives me very, very, very little information. It is really not very useful. All it tells me, honestly, right now, here's what I would assume from the mental sketch. Ready? Since that's the hole right there, look at the graph where I'm pointing, please. The hole is right there. Let me zoom in to make it easier. Since the hole is right here, and another coordinate is here, then another coordinate is here, we know that these graphs have symmetry involved. What do you think the sketch might look like? Mike?
I was thinking it might go like up like that and down like that.
Yeah, good. Curled, exactly like Mike said, up like this, and then down like that. But you need that reflection across something. You see that a lot with these. Now, recognizing also that this is a vertical asymptote, so it cannot be crossed. But a horizontal asymptote can actually be crossed. So don't assume it doesn't. But for now, we'll say that it's probably going to look like this and like this over here. Let's go ahead and figure out how that would work. Okay, how do we know whether we're right or not? We take a look at the graph. Okay, let's take a look at the graph over here. Before we can do that, we plug in our points. Why are these values useful? Give me some reasoning behind them. Why did I choose negative 4, negative 2, 1, 1.5, all those values? How are they useful here? Luca?
Because they increase in between as you get closer to the vertical asymptote.
Yeah. So notice here on the left side of the vertical asymptote. To the left side here, we've got negative 4 we plugged in. We plugged in negative 2. We already have 0, 2 from the y-intercept. We plugged in a 1. We got 1, 3. And then as Lucas said, we went by half of an increment to 1.5, so we can see the almost unbounded behavior of the function. The function growing exponentially, no, I shouldn't say exponentially, it's not exponential, but the function growing at a very, very high rate. Okay, that's the idea. If you plug in 1.75, you probably get a really, really high y value, which would just show you again that this graph is becoming almost vertical. Okay, it's becoming undefined, almost vertical there. And then on the other side of the asymptote's at 2, isn't it? So we go to the other side, and we only go a little bit away. We'll only go to 2.5, just a little bit. And then we'll go to 3, and then we'll go up to 5. So we only go by a little bit at first, and then we take bigger jumps. Clearly the 0.4 kind of 0 is the next intercept, so that's already there. And we have 4 points on that side, and we see the symmetry involved in the graph. Again, the table is what helps you make the graph in the end. What do the asymptotes do? What do the asymptotes do? What do they do? Ben?
Show the boundaries.
Yeah, they pretty much act as boundaries or show the boundaries. Very good. Okay, the intercepts are just easy points to have. They can be no more than actually just graphing the points, right? Technically, just plot points. But the intercept is always determined. Intercepts are important. Here's why. In real-life problems, like word problems that involve graphing, intercepts are extremely significant. It usually means initial value, right? When you have the y-intercept, you're looking at the initial value of something, whether it be a commodity, a resource, a stock, I don't know, profit margin, whatever you're looking at. Maybe an initial length of a spring in physics. Anything, but it's initial value. The x-intercepts are when the value of the function equals 0, which is very important. If you want to know when you have like no profit, or your losses come out to be 0 for that quarter, you want to know when the y value is 0, that's your x-intercept. So it's important that we still practice determining x and y-intercepts, although really, what are they? They're just points on the graph. Okay? And holes we need to know about because of their discontinuities that affect the graph. So we need to know that this graph does not have a value back here. And whereas that value at x equals -7, there is no value of the function. There's also no value at x equals 2. Okay, they're undefined. Example 5 and 6 are both mathematical. Do those together, and then we'll come back together for example 7. Okay, look at example 5. Example 5 is just like the one you did in your homework. You did it twice in your homework, actually, where the whole canceled out, and you were left with some linear function. Read through example 5. Try and make sense of it, but read the actual words. You can work with the person next to you if you want to go over with them. Same as last time, it's fine. When you're done, let me know. If you have a question, let me know. When you're done with example 5, I want you to explain it to me like last time it was. Maybe spend like a minute reading on your own, then turn to the person next to you and talk about it and figure it out. Yes, this is the verb message. Yes. symmetric, right? Symmetry of the graph. You see the vertical asymptote on the other side, and you see those curves, you need your missing something.
Graph that line, it looks like a set asymptote, but the actual function is exactly that. All you have is one. So if you could reduce something as a linear function, it means that everything reduced, there's just holes in the linear function. This happens a lot. You'll have a graph like this, and you'll have several discontinuities on the right, indicating locations where the function cannot exist. So it's literally just a linear function. 1 second.
Day one, right? Anyone else on example 5 who wants to go over it? Okay.
Actually, go for it. What do you want on here? So for example, 5, we start with recognizing first that x plus 4, x plus 4, we cancel each other. Regular factor. There's a negative 4, we have 1. So easy for you, right? Yeah, so you can plug in the hole, you can plug in negative 4, so that's 3 for 4, you can negative 4 is 3, so what you're going to set, so that's the location of the hole.
Then what you recognize is that when you bring the numerator into the denominator,
And that's the only silly for you to view it, so that is that. There's a slant asymptote, right? And when you find the slant asymptote, we're going to have x, which is great, which is really what we have from the 7.5 form. So it turns out the slant asymptote is really the function. The function is on the slant asymptote, the whole on the graph. There's no vertical asymptote because the little factor in the denominator cancels, which makes the whole, so it can't be vertical asymptote. So this is pretty much a line, that whole thing. It's always. Alright, bottom left one. Alright, so the hole's at negative 4, right? When you simplify that, the function just becomes, you go back to equals x minus 3. Right, when you cancel the hole. Now, to find out the location and the height of the hole, you have to plug in the location into the simplified form. So you take the negative 4, which is the hole, plug it into the function x minus 3.
Okay.
Negative 4 minus 3 gives you negative 7. So negative 4, comma negative 7 is the actual location and height of the hole. Now, what else do you notice? There's no other factors in the denominator, once you cancel that whole, right?
See that, with the whole sum, there's no factors in the denominator?
So that means there's no what?
There's no
What is it? What kind? No
No,
vertical.
horizontal.
No, you're right.
Oh, there, in this case, it's no horizontal also.
Yes.
But there's no vertical asymptote because there's no more factors in the denominator.
Yes, it can go on there.
Correct. Now, you also recognize that the degree of the numerator is greater than the degree of the denominator. So it may be tempting to find a slant asymptote here. But if you did attempt to find a slant asymptote, it would just be x minus 3, which is the simplified function we got. So we can't. Yeah, so the function itself is in itself the slant asymptote. It lies on top of the slant asymptote, so there really isn't an asymptote in this problem. So what you have for these cases, this is a very good case for that one. What you have here is a line, pretty much. If you can simplify all the factors and be left with only a linear function, it means you have a line, and wherever you simplify those factors, you have a hole. Okay?
Thank you.
Slide down to number 6, and start working on it. Does not exist. Yeah, so, as long as you do it, remember,
So then there's two, sometimes one at zero, less sufficient for, so you can receive.
no?
And then you can leave it, so if you make x zero, you get negative 4 or 0,
Which is,
does not exist. And then if you set it to 0, then you get 4. So 4 times 36%. And then you put it in forms.
Where the horizontal is.
Horizontal. Well, since it's the horizontal is at 0 because the denominator is greater, I think that what's in the degree of the denominator, so I think it's 0.
so you see clearly you have like 6 regions there, right? So you're gonna have some symmetry there.
And for the points, you always pick around like 0, 45, or negative 44.
Or which is,
Is that just like what a constant?
It depends on the graph, like for example, in this case, if the vertical asymptotes are at negative 8 and 27, then clearly I have to extend the graph. Because my vertical asymptotes are only at what, 0 and 3 or something like that? Yeah, I mean, I don't have to go too much further, I can see the general trend of the graph. But usually, when I make the problems, I know what functions are going to look like, I specifically make them so that they will go a certain way. But for most problems, yeah, you want to behave, you want to pick your values based on the values of the vertical asymptotes. Yeah. Yeah, you have to show me all the work, you check it out. Yes.
Start, finish, stop.
And be able to do this all by hand. And I'm going to allow you to use a calculator to check your work and make a table real quick, so you don't have to do all that annoying math. And you'll be able to do this all by hand and show all your work while doing it. Whatever causes the denominator to be 0 is a vertical asymptote, unless it cancels with the numerator. So nothing cancels here because there's 2 vertical asymptotes.
Would you guess on those? Did you guess on those or like?
You did not get 100
No, on the later ones, like the rock ones.
Well, yeah, so
Oh,
that's
rock
what
is
I
easy.
No, if you do like
I got a second.
some of them, you should guess.
How'd you even get that? Because it was like at 20.
Hey, let's talk about number 6 now. Let's finish it up. So I saw most of you got to the beginning parts of it right. Clearly we factor the denominator, there's two vertical asymptotes here, no hole. Since the degree of the numerator is less than the denominator, there's a horizontal asymptote, it's the x-axis, so when y equals 0. There's no y-intercept, because clearly we have no constant in the denominator. Which would make -4 over 0 if we look at the ratio of the constants. That doesn't exist. Makes sense because there's a vertical asymptote on the y-axis. Let's see that right here. Next, the x-intercept is set in the numerator equals 0, which is 4, 0. That's kind of interesting to think about. Why is it interesting to think about that? The x-intercept is 4, 0. Why does that not seem to make sense right away? Yeah, the x-intercept is 4, 0. Why does that seem to be a little bit odd that we have an x-intercept in this problem? Because the horizontal asymptote, right? It's the x-axis. So we have to remember that we could go through a horizontal asymptote. A horizontal asymptote indicates the end behavior of the function, not discontinuities. So in this case, look at the answer function at the bottom here. You can clearly see right here that we're able to cross through the x-axis. Let's look at the resulting function right here. Okay, so clearly here's your vertical asymptote. Here's your other vertical asymptote. Here's your horizontal asymptote. This middle piece is fine. This piece over here is fine. But here what we notice is that this actually crosses through the x-axis, but it's going to tend toward it, so it's probably going to come back and come back toward the axis over time. So it might cross it, but it comes toward the x-axis afterward, and it'll ride along the x-axis as x gets larger and larger and larger. Okay, remember that the horizontal asymptote and the slant asymptote come from end behavior. It's not a discontinuity. It's not a discontinuity. Only discontinuities we have are holes and vertical asymptotes. Slant and horizontal asymptotes indicate end behavior. It's very important to know that. It's a simple multiple choice kind of problem. All right, example 7. Read through the first 4 things, please, and then stop. Okay, don't do this now, graph the rational function. Just read the first 4, please. Read the properties I want you to have in this function. But obviously you can look ahead, but try not to. Okay, try not to look ahead.
Mr. Hall, did you say horizontal and what, determine
Slant. Horizontal and slant asymptotes are indicating factors of end behavior. All right, so let's take a look at this. We've got several things we want in this function. First, we want to cross the x-axis at 2 and at 4. If it crosses the x-axis there, it means those are the blank. Fill the blank. X-intercepts. If those are the x-intercepts, it tells me blank about the function. If those are the x-intercepts, it tells me the following about the function. We don't know yet. Well, we're only looking at number 1, not number 4, just number 1. It crosses the x-axis at 2 and 4. Just those 2 pieces of information, right? Let's tell me about the function.
they being the numerator?
Those factors become the numerator. And what do those factors look like then? To give me 2 and 4, what would the factors be?
X minus 2 and X minus 4.
X minus 2 and X minus 4, those are in the numerator. So we start by making a fraction with X minus 2 and X minus 4 in the numerator. Next, number 2. Mike?
It's a whole, so it has to cancel both the numerator and denominator, so it means x plus 1 in the numerator and denominator.
Very good. X plus 1 in both the numerator and denominator, because it has to cancel to give you a whole at x equals -1. Again, the whole is at x equals -1. That comes from x plus 1 being in both spots. Ryan, number 3, please.
That really has to be an x minus 6 and x plus 1.
In the? Good. It's got to be in the denominator for vertical asymptotes. So you have x plus 5, which would give you x equals negative 5, and x minus 6. So what we're recognizing, obviously, is that our factors are always the opposites of the values that we're seeing here. It's important to know that. Some of you still make that mistake a lot. I noticed it on the last test that happened. And your factors are always the opposites of whatever the roots would be from that section. And number 4, finally. There's a horizontal asymptote at y equals 3. What would cause a horizontal asymptote? Two possibilities to have a horizontal asymptote. What are they?
The degree of the numerator is equal to the degree of the denominator.
That's one option, and that's what we'll have for here. What's the other option we could have for a horizontal asymptote? What's the other option? When you have y equals 0 as your horizontal asymptote?
The numerator is less than the denominator.
When the degree of the numerator is less than the denominator, it's y equals 0. But in this case, they're equal. Right? We know that the horizontal asymptote is y equals 3. That has to come from the leading coefficient ratio, right? It can't be y equals 0, where the numerator degree is less than the denominator. It can't be the numerator degree is greater than the denominator, because then it'd be a slant asymptote. So the degrees have to be the same. These are all x to the third. How do I know that? How do I know the numerator is x cubed and the denominator is x cubed? How do I know that?
Because there's
Three factors. If you FOIL this out, if you FOIL it out and then triple distribute it into the double distributed there, you get x cubed in the top and bottom. If you multiply all the x's, you just get x cubed over x cubed. So how can I possibly have a 3? What do I need to do to get a 3?
3x cubed over x cubed.
Yeah, we need the numerator to have 3x cubed, don't we? And doesn't the denominator need to be a 1x cubed? Or 6x cubed over 2x cubed? Or 12x cubed over 4x cubed? Or an infinite amount of possibilities? But the ratio of the coefficients needs to come out to be 3. So I need to make this a 3 up here. So I have a 3 in the front of this one in the numerator. So the numerator will become x cubed, the denominator will become x cubed, but now that 3 in the numerator will get distributed to every term, making it 3x cubed over x cubed. Again, it doesn't matter. Instead of 3, I could have made that negative, let's see, 33 over negative 11. What's negative 33 divided by negative 11? 3. It still works. So there are many possibilities for functions here. That's why the next part I put those questions there if you were doing this on your own. What is the deal here? Graph your function. Compare it to a classmate's. How do they differ? So if you tried this on your own and you changed this value, your graph could have differed in its height. It would have been stretched vertically, different than the others. All right, so this is what we have as a result. We have all of our values. What I did for you, you notice here, is when I got to this point, I multiplied it out for you so you could see. So this is what it would look like when multiplied out. But clearly, we can't have x cubed over x cubed. So we multiply everything by 3 in the numerator, which puts the 3 in all these terms, which makes this a negative 15, makes this a 6, makes this a 24, and it becomes this function at the bottom right here. So here's our function at the bottom. This is what it would look like. And look at this real quick. Let's go through the characteristics. Charles, read me the first characteristic that the function needed to have. What was the first bullet point?
It crosses the x-axis at 2 and 4.
2 and 4. Here we go. There's 2 and there's 4. Second characteristic. Niall, what was the second characteristic?
there's a whole when x equals -1.
And x equals -1 is right here. Take a look. Go down. There's the hole. It's probably -1 comma -1 or something like that. Maybe around there. Maybe it's a decimal. I don't know. What's the third characteristic, Kel?
They're very last, so it's at -5 and 6.
At -5 and +6. Well, there it is. And last but not least, Ben?
There's one horizontal asymptote at y equals 3.
And that's the red line right there. Okay, so the graph that we got in the end looks like this, which is exactly what we were shooting for. All right. Anyhow, your homework for this is on the next 2 pages. You can scroll through and take a look. I asked you to get started on the first 2 if you wanted to. If you didn't, it's okay. Okay, but get through these 6, please. Get this done tonight. This is a great way to review tonight. If you can do these problems honestly, you should be pretty much good to go for the test. We should still review E1, 2, and 3, but these all encompass E1, 2, and 3 in them. Okay? So do this tonight, so tomorrow for review, we can look at a few examples, you can ask questions you might still have, and then for the test, you should be pretty set. Okay, it should be high grades on these tests. The topics that we're doing are, cumulative in nature.
Yeah, I'll say it.
Yes. If you want to come after school today, feel free to come by. If you want to even, honestly, if you want to come by and have questions, just want to work on these 6 and ask me questions as you do it, you can do that as well. Because it seems like a lot of people are getting this stuff, but I'd still encourage you to come by after school, spend the time in here working on this, so you can ask me questions instead of at home and then you might be stuck. Okay?